Now I'd like to discuss the regio and stereochemical outcomes for E1 reactions. Regio and stereochemical. Okay, so let's look at a sample molecule. And I have a tertiary chloride. I'm going to react that with ethanol. And we're looking at E1, so we're going to concern ourselves with the elimination product outcomes, but of course there probably will be a substitution product outcome as well. And I also want to identify different hydrogens. So we know that there are several beta positions here. We could say that H1 is right there. I'm sorry, HA, I prefer to use A. This is also a beta position, HB and HC. So let's look at the outcomes with loss of HA. So of course, if we lose HA and we lose the leaving group, we're going to form an alkene at this position here. That would look like that. And the next question is, so that's the regiochemistry, right? Where does the alkene form? It forms between the hydrogen that's lost and the leaving group. So it forms right here in this case with loss of HA. And the stereochemical outcome then is, can this alkene exist as the E or Z isomer, or is it not? It doesn't have any stereochemistry. In this case, there's a methyl here, there's an H that I didn't draw here, there's a methyl here, and there's a 4-carbon chain over here. So we do have different things on each carbon, and we can draw the other version. I'm just going to flip the first methyl up, and then I hope you'll agree with me that I have the E right here and the Z. And these are both minus HA. So that's what we can get by losing HA. Let's look at HB. HB is on this methyl that's pointing downwards. And so if I lose HB and I lose the leaving group, I'm going to form an alkene on this methyl, and it will look something like this. And that's minus HB. Now you ask yourselves, that's the regiochemistry, right? So the alkene is in a different location now before when we compared to minus HA. Is there any stereochemistry associated with this alkene? The bottom carbon has 2 H's on it, and so we can't say that the higher priority group is on one side and the lower priority group's on the other. The 2 H's are identical. There is no stereochemistry there, so that's all we have with loss of HB. Let's look at HC. HC is on the right side. If we lose HC and the leaving group, we're going to form an alkene right here. And let's see, this alkene has, if I just circle the higher priority group, there are clearly 2 different groups on each of the carbons. In this case, the higher priority groups are opposite each other. So this would be called the E version. And of course, I want to draw the Z version as well. To do that, I'm just going to swap groups on one of the carbons. It doesn't matter which one. In this case now, you can see that I've formed the Z version. And then let me label these minus HC. So you can see that this tertiary alkyl chloride has 3 different beta positions that it's attached to. 3 different beta positions means I have 3 different regioisomers. This is one regioisomer, this is another regioisomer, and this is a third regioisomer. So a tertiary alkyl halide with 3 different beta positions should give you 3 different regioisomers. Once you've drawn those regioisomers, then we can establish whether or not we have stereochemical differences, such as with minus HA, so we would draw both isomers, or no stereochemistry associated with loss of HB, so we just draw one. And of course, we're not done. If we wanted to go further, we would draw some substitution products as well. And because there are 3 beta positions here, you should probably have your nucleophile appear at each of those 3 positions. So this can get quite complex, and that's why Sn1 and E1 reactions typically aren't our first choice when we're working in the laboratory. Sometimes we try to avoid them at all costs. However, the discussion of their mechanism, regiochemical and stereochemical outcomes will help us with other reactions later on in the semester. Last bit from this video, I'd like to talk about the stereochemistry of Sn1 reactions. So let's look at a tertiary chloride. And I'm going to draw it like that so that you can watch the leaving group leave, and we can look at both sides of the cation that's formed. So if the leaving group leaves, we would form, it's almost transition state-like. If you remember back from our discussion of the Sn2 transition states, we did draw something like this. Now we're drawing the intermediate in an Sn1 reaction, and it's a cation. I hope you can see the plus charge I drew there. I also drew the empty p orbital, and maybe it might help to draw sort of a plane there to imply that what we're looking at on our screen is this planar cation perpendicular to the screen. So the p orbital is in the plane of the screen, the ethyl group is in the plane of the screen, this methyl is projecting towards you, and this isopropyl is projecting back out of the screen away from you. So we're looking at this planar thing from the edge on. There's also a chlorine here, and we know it's right there because it started on the right side of the molecule before it left. So it's still going to be in close proximity before anything happens or any time goes by. And so we call this an ion pair. And this ion pair actually serves to hinder the nucleophilic attack. And so let's say we're using water as our nucleophile. Let's put water right here. It's ready to come in and attack the cation. And I'm going to use two different colors to show the attack. So we could have an attack from the right side near the chlorine, and that would give us this intermediate. With the nucleophile entering from the right side, and we could have attack from the left side, and that would get us this intermediate. Where we have attack by the nucleophile from the left side. And it turns out that we don't get a 50-50 ratio of these two intermediates. So we don't get perfect inversion here. We get more of the purple intermediate, and we get less of the green intermediate. And that's because the leaving group tends to protect or shelter or shield, in this case, the right side of the molecule. I should say the right side of the cation. So the fact that we form an ion pair immediately after losing the leaving group, that serves to influence the stereochemical outcome of the reaction. The leaving group is going to block partially, not a lot, but partially attack via the green arrow in this case. And so that means we'll get less than 50% of the nucleophile adding from the right side. And I'm not saying we get 25% of this ion and 75% of this, but maybe it's 45 to 55, or even 47 to 53. So it's slightly out of balance, but it's not very far out of balance. And that's the result of this ion pair here. So most of the time, an Sn1 reaction does not result in perfect racemization of our chiral starting material as we had here. It results in an uneven mixture of the enantiomers. A little bit more from the back side and a little bit less from the leaving group side.